Good morning, one and all. Today we are going to see about the symmetrical component transformation. Symmetrical component transformation in the continuation of the previous class. Already we are seeing this positive, negative, and zero sequence components. So here we are seeing the three-phased unbalanced circuit current. What is the three-phase unbalanced circuit current is represented as IA, IB, and IC can be expressed in the terms of sequence current. Sequence current in terms of here positive, negative, and zero sequence. So IA is equal to IA 0, that is a zero component there, plus IA plus IA minus. Next, IB is equal to IB naught plus IB positive plus IB negative. Next, IC is equal to IC naught, IC plus IC negative or IC minus. So these are the positive, negative, and zero sequence component. So zero also you can tell, or not also you can tell. But this is the expression for the currents, three-phase unbalanced current. So according to the definition of symmetrical components, so symmetrical components, what we are doing is we are converting all our like phase quantities like A, B, C in terms of A component, phase A component. So that is your symmetrical components theory. That is a sequence operator, A operator. What is the significance of A operator? How to change the A operator? How to change all the phase components with the A operator? Like already we have seen in our previous class. So according to the symmetrical components, so what we are doing is we are rewriting all this phase current in terms of your IA, like A component, A operator. So IA is equal to IA naught plus IA plus IA negative. Next, IB is equal to IA naught plus A squared IA plus. So how A squared IB plus is equal to, say, for example, in that phasor diagram, so IB plus in other terms, how can we write in the sense? So it is 240 into IA plus. Next, plus A into IA negative. So here IB minus, how can we rewrite in terms of IA now? It is 120 degree of IA minus. So 120 degree we are converting into A. So A IA minus. Similarly, IC is equal to IA naught. This IC naught is equal to IA naught. IC positive is equal to A IA positive. So how A IA positive in the sense IC in other terms we can rewritten as 120 degree of IA plus. So 120 degree we can take it as A. So A into IA plus. Next, IC minus we are rewritten as A squared into IA minus. So what is A squared? A squared is 240. So IC minus we are rewritten as 240 of 240 IA minus. So A squared into IA minus. So what we are doing is we are rewriting this above equation in terms of matrix format. So matrix format here IA, IB, IC. That is the phase components of the current that is equal to here. What we are doing is we are taking the common term IA naught, IA plus, and IA minus outside. So here you'll get as 1 A squared A 1 A squared. So all this this coefficients we are writing here and taking the common terms outside IA naught, IA plus, and IA minus. So if you multiply this, you'll get the same answer. If you multiply this matrix, you'll get the same answer. So we are written in the matrix form. So here IA, IB, and IC are the phase current. So IP. So we are taking the common term as IP. This matrix we are taking as T. T is nothing but symmetrical component transformation matrix. Symmetrical component transformation matrix. Here IA naught, IA plus, and IA minus. This matrix we are taking it as IS. So IS is nothing but sequence current. So we are representing in a common term as IP matrix is equal to T into IS. What is IP? IP is nothing but IA, IB, and IC matrix. What is IS? IS is nothing but sequence current. That is nothing but IA naught, IA plus, and IA minus. Where T is the symmetrical component transformation matrix. That already I have explained. Next, symmetrical components of currents from the phase current. So what we are doing is here, we are taking the phase current, that is IS outside, IS out. This is the generalized format, that is IP is equal to T into IS, T matrix into IS. That is the generalized format. Here, what we are doing is, we are taking this IS outside. That is a sequence current we are calculating. How to calculate? So this, if sequence current come out means this will come in inverse. So IS is equal to IP inverse into T, or T into IP inverse. That is what here they written. IS equal to T inverse into IP. T inverse into IP. Here, symmetrical component of current IS matrix we already know. That is IA naught, IA plus, IA minus. T matrix also we already know. 1, 1, 1, 1 A squared A, 1 A squared into IA, IB, IC. So IA, IB, IC is nothing but this phase current matrix, this matrix. Now, A matrix, A inverse equal to 1 by modulus of A into adjoint of A. Here it is T inverse. So T inverse equal to 1 by modulus of T into adjoint of T. First, you need to calculate what is the modulus of T. Modulus of T, how? First, we are taking this first term 1 outside into this A power 4 minus A square. A power 4 minus A square. A power 4 is nothing but A. How it is A means A cube is equal to 1. A cube, how it is 1? A is equal to 120 degree. A square is equal to 240. A cube is equal to 360 degree. 360 degree. How we represent 360 degree? 1 at the angle of 360 degree. 1 at the angle of 360 degree is 0 degree. 360 degree is nothing but a 0 degree. So 0 degree has no value. So A cube is equal to 1. So here A cube is equal to 1 means A cube into A is equal to A power 4. So 1 into A is equal to A. So A power 4 is equal to A. Here A power 4 is equal to A. So you need to substitute A power 4 as A. Similarly, next component. So here minus 1. So this you need to neglect. This 2 you need to neglect. A squared minus A. So A squared minus A. Plus here 1 into here A minus A square. A minus A square. Simplify this. You will get the after simplification, taking the common terms outside, you will get a 3 into A minus A square. So students, you take as a homework, just calculate it. You simplify it and accordingly you just take the common terms outside. So 3 into A minus A square. So T inverse is equal to 1 by modulus of A, that is the adjoint of T. Adjoint of T, how to calculate? Adjoint of T, yeah, here the same thing. Adjoint of A is nothing but this A power 4 minus A square. Here A power 4 minus A square. So here also that this thing, if you neglect A squared minus A squared minus A minus of. So minus of means A minus A squared. That's all. So similarly for all adjoint of A, you know how to calculate. Similarly for all, you need to calculate, and simplifying this A minus A square. A minus A squared. So I think everything A minus A squared is common. I think you in the division also A minus A squared is there. So just take your just substitute this in inside A minus A squared divided by A minus A squared. So this becomes 1. So here 1. So similarly for all, you need to substitute here and taking the 1 by 3 outside, just simplify here and you'll get the matrix like this. 1, 1, 1, 1, A squared, 1, A squared, A. This is the T inverse matrix. The symmetrical components of current, just you need to substitute this because T inverse, you know, the same thing. Here you need to substitute this inverse value, you know, T inverse value, you know. So just you need to substitute this value here. After substituting, you'll get like this. IA 0, IA positive, IA negative, matrix is equal to 1 by 3 into matrix of 1, 1, 1, 1 A squared, 1 A squared A into IA, IB and IC. So this is the symmetrical components of current matrix. Now, again, what we are doing is we are taking the zero sequence, positive sequence and negative sequence separately and we are writing. Just multiply it, you'll get IA naught is equal to 1 divided by 3 into IA plus IB plus IC. Next, IA positive is equal to 1 by 3 into IA plus A into IB plus A squared IC. Just multiply this matrix with this matrix. So you'll get the answer like this. Next, IA minus equal to 1 by 3 into IA plus A squared IB plus A into IC. The zero sequence current is equal to the 1/3 of the sum of the phase current. Zero sequence current is equal to 1/3 of the sum of the phase current in a three-phase with the ungrounded neutral. Say, for example, in a three-phase, if the neutral is not grounded, in a three-phase with the neutral is not grounded, then IA plus IB plus IC is equal to 0. So that is nothing but you can take it as IA naught. IA naught. So here IA plus IB plus IC is equal to 0 when the neutral is not grounded. Just substitute this in this first equation. That is IA naught is equal to 1 by 3 into IA plus IB plus IC is there now. Just substitute here. So you'll get IA naught is equal to again 0 because 1 by 3 into 0, that is 0. That is the zero sequence current does not exist in the three-phase ungrounded neutral. So zero sequence component will not exist in the three-phase ungrounded neutral. That is also it is a noted point. Next comes the voltage. So we did previously we did for current. Now we are doing for voltage. That's all. Same equation. Only notation only changed. Instead of IA naught, here VA. Instead of IB, here VB. Instead of IC, here VC. That's all. Same equation, same thing. In exams, they may ask to derive for a symmetrical components current and as well as symmetrical component voltage. Sometimes separate also in only voltage. They may ask in 5-mark question like that. Anything you can write because same equation. Here, unbalanced phase voltage in terms of symmetrical component voltage. Let VA, VB, VC, similarly like IA, IB, IC be the phase current. Here, VA, VB, VC be the phase voltage and VA not VA plus and VA negative be the zeros, positive and negative sequence voltage of the phase A. So here, what is VA? VA is equal to VA naught plus VA minus. Similarly, VB is equal to VB naught plus VB minus. That means phase current which consists of all your zero, positive and negative sequence voltages. Similarly, VC is equal to VC naught plus VC plus VC minus. Now what we are doing is we are converting the same thing into A component. A, B, C into A component. So VA is equal to this VA naught plus VA plus VA minus. Here VB is equal to VA naught plus instead of VB positive in that phasor diagram, VB positive nothing but 240 of VA plus. So A squared into VA plus VB negative is equal to 120 of VA minus. So A into VA minus. Similarly, BC. BC is equal to here VA naught plus BC positive is equal to A into VA positive. BC negative is equal to A squared into VA negative. Here we are rewriting in the matrix format VA, VB, BC is equal to, here we are taking the common terms of like positive, zero, negative and zero sequence components outside. VA naught, VA plus VA minus matrix outside. So you'll get the matrix like this: 1, 1, 1, 1, A squared A, 1 A squared. Same like that, only notation only changed for voltage. Same for current also, same equation. Here VP phase matrix is equal to T into Vs. Here what is T? T is nothing but symmetrical component matrix. Here 1A, 1, 1, 1, 1A, A squared A, 1A, A squared. This is the T. Here what we are doing is we are rewriting this phase component in terms of A, B, C. B, A, B, C is equal to T matrix into V of 0, 1, 2. 0, 1, 2 is nothing but positive, negative, and zero sequence. So, okay, 0, positive, and negative sequence that can be written as 0, 1, 2. Sometimes in exam, what they will do is convert this phase quantities into your 0, 1, 2 components. Prove that convert phase quantity into V0, 1, 2 also, like that also they may ask. Instead of what do you call? Instead of this zero positive and negative sequence component, they may ask you to derive, convert the phase voltages to your VA 0, 1, 2, 3. Sorry, VA 0, 1, 2. Like that also they may ask, like a question. Same answer only. The question alone they may ask in different way. So instead of zero positive and negative, you can also use 0, 1, 2, 3, or otherwise you can use the same notation. At last, you may write the one conclusion like we taken instead of the 1, 0, 1, 2, 2. Here we have taken as 0 positive and negative, so that this equation can be rewritten as we have 0, 1, 2. Like that also you can write. Nothing wrong in that. For a current also they may ask the same. Convert the phase quantity into zero. This zero like phase components. Okay, phase component into this zero positive and negative sequence components. That is sequence voltage components. Like that also they may ask. Next is symmetrical component voltage in terms of phase voltage. Same story here. What we are doing is, in this notation is there now, VP is equal to T matrix into Vs. So we are taking this Vs outside. So T inverse of VP. So T inverse of VP, where Vs is equal to VA naught, VA plus VA negative. That is your sequence voltage. That is equal to this T matrix 1, 1, 1, 1 A squared A, 1 A squared, the whole inverse into this phase voltages VA, VB, VC. That's all. So this inverse, this T matrix inverse, already we have taken the same inverse in the previous equation. The same answer you can take. The same answer only we can come. But if not, in exam separately maybe ask. So don't write like similarly for current we solved like that. Don't write. Here you need to calculate this modulus of T and T inverse. Then you substitute and you derive and you substitute, and the final answer you write. Don't write similarly. We do it for symmetrical, because in exam separately voltage alone might be asked. So that time you need to derive all these things here also. And after taking the inverse, you will get the matrix as 1 by 3 into 1, 1, 1, 1 A squared, 1 A squared A. So compared to this, only this alone will be changed. This alone will be interchanged. That is A squared A to here and A to here, A squared here and A as here. So this you need to remember but you need to derive and you need to like take the inverse and you need to just check. For checking, you can remember like this. But in exam, don't simply like this, because sometimes 5 marks also there. If 2 mark they may ask, then you can write like this. Nothing wrong in that, because 2 marks it will take more time, much of the time. So if 2 mark is asked, you can directly convert this matrix like that. But in 5 mark, you should not do this mistake. Here, Vs is nothing but sequence voltage and Vp is nothing but phase voltage. Next comes the apparent power. Apparent power in terms of symmetrical components or power variance. Same apparent power. What apparent power? Yes, three phase. Three phase apparent power is equal to Vp, the whole transpose into Ip star. Ip star is nothing but the complex conjugate. Here, if you are converting into complex format, that J component will come in the negative. Okay, like imaginary component will come in the negative. That is the conjugate, complex conjugate. Here Vp, the whole transpose into Ip star. Here also what we are doing is we are rewriting in terms of single phase. Rewriting in terms of a single phase. So here Vp transpose equal to T into Vs transpose, because already you know Vp is equal to T into Vs. So here you are substituting T into Vs transpose. Here Ip is equal to T into Is from the previous formulation. Yes, star. Here taking it outside Vs T transpose T star Is star. Here T transpose into T star. T matrix already you know that you substitute and make take transpose into T star. If you multiply that, you will get the answer as 3. You can also take it as a homework and you can try. So T transpose equal to T. So T into T star is equal to 3. Next, apparent power 3-phase components equal to 3 into VST, that is Vs transpose into Is star. So here we are rewriting in terms of sequence voltage and as well as the sequence current component. Here the equation becomes 3 into VA naught IA naught star plus 3 into VA plus IA plus star plus 3 into VA negative IA minus star. This is the total unbalanced power that can be obtained from the sum of the symmetrical component powers. This is nothing but a total unbalanced power, that is apparent power, that is obtained by the sum of the symmetrical component power. This is all our power, because VA not into IA is nothing but power. So that is what they said. It is a sum of the symmetrical components power. So apparent power also. Sometimes 2 mark they may ask apparent power. Write the apparent power in terms of the symmetrical components or power variance, variance of power.